Have you ever looked up at the night sky and wondered whether we are truly alone? Today, we explore exoplanets, worlds orbiting stars far beyond our solar system, and the discoveries that are bringing us closer to answering this timeless question. Just 30 years ago, the existence of exoplanets had not yet been confirmed. Detecting even a single planet around another star was considered an extraordinary challenge. Today, thanks to advances in observational astronomy, scientists discover new exoplanets every month. One of the most powerful techniques is the transit method. When a planet passes in front of its star, it blocks a tiny fraction of starlight, causing a subtle but measurable dip in brightness. Space telescopes like Kepler and TESS monitor millions of stars, searching for these repeating signals, the shadows of distant worlds. From these observations, astronomers can determine a planet's size, orbit, and distance from its star. But discovering a planet is only the first step. To understand whether a world could support life, scientists must study something far more delicate: its atmosphere. As a planet transits its star, a small portion of starlight passes through the planet's atmosphere. Different molecules absorb light at specific wavelengths, leaving behind a unique chemical fingerprint known as a spectrum. The presence of water vapor, carbon dioxide, oxygen, or methane can reveal critical information about temperature, chemistry, and potential habitability. This marks the beginning of a new era in astronomy. The James Webb Space Telescope does not simply detect atmospheres, it analyzes them in detail, measuring their composition, structure, and temperature with unprecedented precision. Although we cannot yet directly observe the surfaces of these distant worlds, the data allows scientists to model realistic conditions and evaluate whether environments similar to Earth might exist elsewhere in the universe. So what makes a planet potentially habitable? First, it must orbit within the habitable zone where temperatures allow liquid water to exist. Second, it needs an atmosphere capable of retaining heat and shielding the surface from harmful radiation. And third, it must be a rocky world with a solid surface, not a gas giant. Several real exoplanets already meet many of these criteria. Proxima Centauri b, the closest known candidate, orbits the star nearest to our Sun. It is a rocky planet slightly more massive than Earth and lies within its star's habitable zone. However, its parent star is an active red dwarf, producing powerful flares that may threaten the planet's atmosphere. Another remarkable system is TRAPPIST-1, located about 40 light-years away. It contains 7 rocky planets packed into extremely tight orbits. Some of these worlds lie within the habitable zone and may possess liquid water beneath their atmospheres, even if they are tidally locked. Farther away, Kepler 452b orbits a star similar to our Sun and receives nearly the same amount of energy as Earth. Often called Earth's older cousin, it may have a thicker atmosphere and a warmer climate. Another promising candidate, TOI 700d, orbits a relatively calm red dwarf star, increasing the chances that it has retained a stable atmosphere over billions of years. And LHS 1140b, a dense rocky planet, may even host a global ocean beneath a protective layer of ice. None of these planets has yet shown direct evidence of life, but they are not theoretical ideas. They are real worlds with measured masses, known orbits, and observable atmospheres. Each one is a natural laboratory where chemistry, energy, and time may interact as they once did on Earth. The universe is not silent. It speaks through light across immense distances and deep time. And for the first time in human history, we are learning how to understand that language. For now, all we can do is look upward and wonder whether, somewhere around another star, someone is asking the very same question.